first session is going to be perspectives from the air. Everybody in this business knows that we love taking pictures from space, but every so often we may not get the coverage we need with the phenomenologies we need for the dwell time, with the mission support that we need, and air serves a purpose that simply can't be replaced. So we're going to start with someone we have a little familiarity with, Dr. Andrew Shepard from Unmanned Aerial Systems at Sinclair Community College. All right, do it.
Well, hello again. So I'm glad to be back to talk about a few other activities we have going on. One thing that I learned after we got off the demo was that Dave Chappelle was taking off from the airport we were flying at, so we were waiting on his jet to get launched, and so that's things that happen in live demos. So fortunately it didn't affect anything with the schedule, but kind of a cool fact of the day. Another thing that I was going to kind of call out as we're getting started here on the next part of our highlight reel is that with beyond visual line of sight, that's still, for UAS operations at least, a regulated and restricted area that the FAA, the Federal Aviation Administration, is still working through. You have to ask special permissions to be able to do things like that. And so things like we talked about earlier with LVC allow you to advance that technology and capability for all kinds of applications like mapping and geospatial. But what we're going to be talking about now are basically things related to unmanned aerial system, civil and commercial applications that do not currently require a waiver from the 14 CFR Part 107 regulations that came out in August of 2016. So as a quick recap, we'd been operating under the paradigm earlier to that. You had what were called certificates of authorization. They were special waivers that the FAA would issue to public operators to fly UAS in the National Airspace System. Those were originally developed for really the military, and then they were expanded and you were allowed to do it as a public college like Sinclair. And then a few years ago, they came out with a public law that said, it was called Section 333 exemptions, and those allowed commercial entities to fly UAS in the national airspace for commercial purposes. And then in August, they came out with the 107 regulations, and that really is the new way forward. Now, there's permissions you can get for waiver to that, so if you want to fly higher than 400 feet, faster than 100 miles per hour, weights more than 55 pounds, beyond visual line of sight, nighttime operations, you still have to ask for special waiver. But the bulk of what most people are trying to do in UAS today, let's say the 70% solution, is kind of covered under the 107 regulations. Sinclair is a member of the FAA UAS Assure Center of Excellence, the UAS Center of Excellence, and we're also a member of the National Science Foundation Center for Unmanned Aircraft Systems. And those are kind of two different national centers. The FAA is interested in implementation and safe integration of UAS, and we advise and consult and advance that. And then on the other side with the NSF, they're interested in commercial applications and technologies. Something that's a nice mixture of those two activities are what we call Pathfinder activities. Over the last year, we've done several of those for the state of Ohio and in partnership with federal partners. And so what we thought we would highlight here are a few of those. Specifically, some work that we've done on open pit mines, bridge inspections, road inspections, airport infrastructure, oil well pad and commercial spills, and then harmful algae blooms and toxic algae up over Lake Erie. So I won't have a lot of time to dwell on any of them, but it's a little bit of a highlight of what you can accomplish using commercial off-the-shelf UAS technologies, sometimes with some system integration required in the current regulation environment. So all these activities are accomplishable without having to go through a waiver process at this point. So as we're kind of going through the slides, my transitions, you'll see kind of a dark arrow pointing to the next one we're going to. So we got the pit mine up first. And so I thought rather than a bunch of words on a screen, I would kind of give you some representative images from each of those activities. When we worked with the Ohio Department of Natural Resources through the Ohio UAS Center and Test Complex, they asked us, can you look at several application areas of interest for us? One of those, first being a pit mine. This was over in eastern Ohio in the Vinton County area. And this is a Ohio Department of Natural Resource managed and leased facility. They were interested in using commercially viable, relatively low-cost UAS today. Could you map and assess that property, several hundred acres, at a reasonable deployment cost and turnaround time? And so we took out what was called an Altavian octocopter. It's called an R8700. And so that was our GIS mapping platform that had a 29 megapixel nadir pointing mapping camera in it. We also flew a Kestrel and a few other video downlink aircraft. And so it allowed us to, the video aircraft were giving us a sense of situational awareness of the site, visual inspection capability. The nadir pointing aircraft were allowing us to do condition assessments, volumetric analyses, and actually develop georeferenced mosaic imagery and then eventually 3D models of the entire site. And so that was a great application. Really, you could do the whole facility in about a day. Department of Natural Resources was definitely interested in continuing that kind of a exploratory project, and so we're going to have some follow-ups I'll talk about very quickly at the end. In the interest of time, moving on to the bridge. So this was the first time UAS were flown for a infrastructure inspection like this in the downtown Dayton area after Part 107 came out. This was in the fall of last year. You'll recognize our mobile ground control vehicle. We were flying both commercial off-the-shelf inspection equipment, but also some interesting integrations. We had a panoramic COT sensor that we integrated into one of our aircraft for under-bridge inspections. We were doing the 3D modeling from the nadir imagery, and Altavian actually brought up a prototype infrastructure inspection aircraft that we tested as well. So this was to do three things really. It was a road deck inspection, surface assessment, visual inspection of the bridge itself, concrete delamination, rust of metal and connection points, and then also structural integrity and then the surrounding area. So it was a combination of visual, video, live inspection, and post-mission analysis, 3D modeling, and georeferenced imagery. Again, moving along to our road inspection. This was a lot of concept of operation development. So the road was actually Ohio's test track. It's up near Marysville, kind of to the northwest of Columbus. And one main application area at this facility is Honda does a lot of their aircraft or their vehicle testing, their car testing there. And so it took about 4 months just to get through all the paperwork about we're not going to be doing corporate espionage at the facility on the vehicles that were going to be on site. So there was some negotiation that occurred about we're just going to do nadir aircraft mapping at that facility. And what we were primarily interested in is could you determine where you might need to do road repair. So where were there cracks? How bad were the cracks? Did it meet a level that you needed to come back and do a repair? And so we had various levels of resolution that occurred, again, flying an Altavian octocopter. So that system's about a $15,000 aircraft with about a $5,000 sensor in it. So for $20,000, you're getting higher quality resolutions at this and the other sites that we're talking about than you could get with a traditional manned aircraft system, and you're doing it much faster than you'd be able to do it with a ground-based inspection. Now, UAS is not always the best tool, and that's part of the reason that we do these applications. Is we want to say, well, I'm a U.S. advocate, but if it's not the best tool or it shouldn't be the only tool, you need it as an augmentation. That's another thing together. So kind of moving along to the airports, we actually did 2 airports. The first was Springfield, where we did our LVC demo from today. This is now an uncontrolled airspace. It used to be a Class Delta controlled airspace. And so you kind of get a sense there, again, mapping flights of runways, paved taxiways, apron areas, nadir shots to create 3D models and virtual point clouds of airport infrastructure like the air traffic control tower, the hangars, the tenant facilities, and also you can see the 3D model of the nav aid. They got a VORTAC there, and so the bottom center image is imagery from it, and the bottom right image is actually a 3D model that was constructed from the imagery. So we had some nice products that came out of that. Actually, we were giving them information back to the airport that they used about needing to get a state grant for repaving one of their taxiways. runways. So a lot of good flight operations there. Again, fixed wing Altavians, octocopters, quadcopters, video inspection, mapping missions, and so on. That was at Springfield. At Wilmington, we actually had some other infrastructure that we could work at. So we had oil and fuel storage tanks, warehouses, parked aircraft from commercial aircraft operations, nav-aid inspections, rapid lights, again 3D modeling and nadir mapping of the runway environments, and even doing simulated visual approaches coming in on the NOTAM closed runways. So a lot of really good interest there for the state of Ohio and really for others. The oil well pad inspection, this was interesting. Again, there were some corporate security issues, so Gulfport Energy requested that we not take ground photography or record aerial video or imagery over their well pad. It was a visual inspection for live assessment of site, so I can't show you anything of the well pad itself. But the second activity that we did was actually the Ohio Environmental Protection Agency did a dye release into an adjacent creek, and then they were interested in a very low-cost UAS application of a visual inspection of that dye release. Could it be seen from the air with minimal training? And it turns out that it was quite visible. So Ohio EPA was happy with that product, as was Gulfport Energy. So in all of these application cases, we had always a local partner like Gulfport, like the airport, like the pit mine operator, the city of Dayton municipality for the bridge, and then we had a state client or a state partner that was interested as well, with the Ohio UAS Test Center as kind of the enabling organization. As we're moving forward to the last highlight, harmful algal bloom. So this was a collaboration with the NASA Glenn Research Center. We integrated what was an 8-pound hyperspectral sensor. We pared that down to a 4-pound sensor, got it integrated into our Altavian aircraft, had to 3D print the sensor housing and the blister canopy, integrate everything, do weight and balance up at NASA, EMI testing, had to do calibration flights. This is a 260 band hyperspectral sensor, so we were flying that down at Wilmington Air Park first, getting all the sensor tweaks put in, and then we went up to Lake Erie and flew out over the Maumee Bay, which is close to the Ohio, Michigan area, and had University of Toledo doing water samples as we were flying, so we had some ground truth. And actually that bottom right image, we were manually landing it, so you're actually reverse controlling the aircraft flying towards yourself, so if you mess up, it's gonna fly right through your tent, so there's no stress. But it was a really good project, and NASA actually has requested that we do 12 more days of lake flights with them as a follow-on project this summer. So again, as I mentioned earlier, just quick synopsis, we're really interested at Sinclair in those applications of existing or soon to be commercialized technologies, getting those out into real world applications and making them useful for everybody out there in the commercial and government world. So I know there's other speakers behind me, so if there are any questions or follow-up interest about any of these or other applications, again, we'll be at our booth for the rest of the show, and thanks for the opportunity to speak to you again. So have a great show.
Great, thanks. Thank you, Dr. Shepard. So as Dr. Shepard said, UAS are fantastic tools, but they're not appropriate for everything. Our next speaker will be talking about some manned fixed-wing missions. And just like our previous speaker talked a lot about electro-optical, right? That tool, electro-optical imagery, isn't necessarily always the phenomenology that you want to use for all your applications. And LiDAR is one of those phenomenologies that has taken the world by storm over the past, I'd say, at this point, we're almost at 20 years now. And we've gotten to the point where next generations of the technology are emerging that are opening up new frontiers for us. So the gentleman who's getting ready to come up on stage is from Harris Corporation's Geospatial Solutions, and he's the senior product manager. He does not have a doctorate, but many people with doctorates work for him. So you be the judge. And let's introduce Mark Romano to the stage.
Good afternoon. I really appreciated the sci-fi pictures a little bit earlier. We're going to talk today about Geiger mode LiDAR. And this is not science fiction. In fact, there's a lot of discussion about commercial access to sensor data, and this is actually a commercial sensor we're going to talk about. Just a quick review from the audience. Is anybody in the audience using LiDAR in their mission today? Could I get a raise of hands? Quite a few. Anybody with Geiger mode LiDAR background? I knew I'd only get a few of those, because unless you were a part of the privileged few using it on the inside of the defense industry, you probably never heard of it before. So hopefully we can educate you a little bit today. For those that are familiar with conventional technology, the Geiger mode technology is now commercially available primarily because about 4 or 5 years ago, the government allowed the key components to be declassified and allowed commercialization of some of the key components. I'm going to get a little bit more into the data here in a few more minutes. This is going to be a lot of geek speak and some pretty pictures, so bear with me. But it is not a new technology. In fact, it dates back to the early 2000s and was specifically developed for foliage penetration capability back in the day in a targeting mode. And we've also got some high altitude systems that have been deployed over the past several years that were for long range standoff distances to look across borders and other types of defense applications. And I apologize for my voice today, I'm losing it. Not for your benefit, but maybe some of my Harris brethren later will appreciate that fact. So what is it? If you consider in this example here, conventional LiDAR, if you're familiar with it, is a very low altitude, slow type collection system. These are both active systems. Geiger mode LiDAR, at least up to the altitudes we can talk about, and this commercial technology operates over a range of about 6,000 feet above ground to up to 35,000 feet above ground. So the biggest difference, and you've seen a lot of discussion of UAVs, you've seen probably some of the mobile LiDAR technology, small LiDAR sensors on UAVs, airplanes, trucks, trains, you name it. We've deployed them in the terrestrial and airborne environment now for probably over 20 years. The difference is those are what I call a low and slow system. To get high resolution, we fly them pretty low to the ground, and they're direct measuring with a single point or beam of light, which I'll explain in the next slide. The Geiger mode technology is sometimes referred to as photon counting. So it's a high sensitivity, low power requirement type of a system. So this is just a simulation, just to give you a little bit of a concept of how a conventional scanner technology works. So, and this is a simulation of trying to get about an 8 point per meter type of resolution. So it's flying low, it's flying slow, it's got a narrow swath, whereas the Geiger mode sensor is flying very high on a very fast moving aircraft, or even a jet aircraft if necessary. So it covers a lot more ground, a lot wider, a lot faster, and at a lot higher resolution. Excuse me. So what is this thing? It's actually a camera. Not unlike your cell phone, they started out very small. Everybody's got one of these by now, unless you're still using a flip phone. Very few. So you know that over the years, this technology has gotten higher and higher resolution as the imagers scale. Well, that's what's happening to this technology. So it started out in very small pixel arrays. Now we're working on a 32 by 128 array. And next year there'll be 128 and 256 by 256, and it'll continue to scale. So this technology is going to really be a game changer, not just for airborne applications, but for also terrestrial applications. Conceptually, if you look at it, again, if you're familiar with conventional LiDAR and you look in the lower left, you can see that it's a scanning system and it's firing a single ray as it scans back and forth. Or we'll use a spinning polygonal mirror sometimes as well. But you're direct measuring certain points on the ground as you're flying forward. The Geiger mode technology doesn't illuminate a single ray of light. It actually illuminates a large area, and you're getting elevation, think of it as a camera, frames of elevation data. So you're illuminating a large area and getting frames of data. And we're using a Palmer or circular scanner, as you can see in the image to the right, which is showing you a very small subset of one scan. So instead of direct measuring, we don't set up to collect at a specific resolution. We're collecting many, many frames of information, which we can adjust the side lap and the forward lap, or the amount of, I'll call it oversampling, we can do as we fly over a scene. So we don't collect at a resolution, we actually process to a resolution. And it's uniquely different in that we're doing signal processing to achieve the point cloud or elevation data set. If you consider conventional scanners, these are just some examples of what you would see. So you can see the scanner is moving back and forth, and you can see you're going to get occlusions behind buildings. Also, when you're coming through heavily forested or heavy land cover canopy environments, you're only going to get one probable shot at one angle as you're coming down through the canopy and flying forward. So again, you're going to get some occlusion, and you're going to have a lower probability of actually reaching the ground or assets you might be interested in seeing beneath the canopy. The other thing you're going to notice with a conventional technology is what I call compression or expansion or non-uniformity, which you'll see due to aircraft movement, because you're only flying over it once, and you're only visiting the ground as you scan across one time. The way we solve that with Geiger mode is we're picking up objects on the fore and the aft of the Palmer scanner and oversampling it, and we fly it in both directions. So you're almost getting a 360-degree object view. You're improving the probability of detection of an object from all sides, excuse me, and you're improving your ability or probability of detection through and beneath heavy canopy environments. So just another conceptual way of looking at it, if you consider a single object, I've sampled it hundreds and hundreds, sometimes with thousands of pixels or elevation frames. So these are very high sample rate systems, much larger data. So we don't operate in the Windows environment like a lot of the conventional technology does. All of our data comes in raw. It's ingested into our distributed processing center. We can also deploy this as a forward PED, or you can also build actually real-time processing systems on board an aircraft if you wanted to achieve that in a more of a real-time way. In Palm Bay office, where I'm from in Palm Bay, Florida, we have a 3,500 core distributed processing center. So a lot of processors, a lot of storage to deal with some of these systems. Just a little bit about accuracy. I gotta watch my time here. This was a test we did 3 years ago when we first commercially deployed this. We flew it at 26,000 feet. We can collect 500 square miles in a single evening. And what you're seeing with the green dots is the automated bundle adjustment process. So this is all hands-off processing. And because we have 4 looks from the way our scanner collects data, we get a very robust precision within data blocks. And we're typically processing in 500 to 1,000 square mile data blocks. And with this particular test, which was an independent assessment, we hit an accuracy of 5 centimeters, if you think about that, from 26,000 feet. And that's machine processed. So what does all this mean? Now to the pretty pictures. On the left, this is a linear mode collect, something you typically would be used to working with, from 3,200 feet. On the right, you're looking at a Geiger mode image at 12,000 feet, flown much faster, much more uniform. And if you look a little bit closer, you can actually see where on the left-hand side, you're really not picking up the sides of the object because you're only getting one look. So you're going to get that occlusion, right, on one side or the other, or sometimes more than one side. Because we're looking at it from 4 different angles, you're going to get a much higher fidelity image. It's processed in voxel space, so it's more uniform. It's not as random. And you're going to get all the sides of the buildings in a very, very high level of detail. Looking a little closer again, this is from 17,000 feet, processed at 30 points per meter resolution. You can see 3-inch parking stripes You can see poles, wires, crosswalks. And again, when you think about the GEOINT mission, right, we're not flying in space, so we're not exactly out of harm's way in all circumstances, but flying at a couple of key safe altitudes for government customers is above 17 and above 25. And we can achieve these types of resolutions at those altitudes very fast. Foliage penetration, again, remember that with a conventional scanner, you're approaching a canopy, you're scanning at one time, you're getting one angle of approach, and you're sampling at once. With Geiger mode, you're oversampling it, you're measuring it from multiple directions, and you're going to get a very high probability of detection beneath the canopy. So what you're looking at here, this was a 12,000-foot flight. That's a 1-foot slice through that very heavy tropical canopy environment, and there's a lot of ground beneath it. So when you're building terrain models or looking for assets under canopy, this is an ideal system to try to achieve that. Just a couple of quick visibility analysis. Again, high resolution, high accuracy, high altitude, wide area coverage. Very precise analysis. Another image here, similar thing. As you zoom in, again, you're going to get very precise about what an observer can and can't see from multiple angles, and you can run these types of analysis very quickly. HLZs, again, not a new product to anybody here in the Intel community, but again, it's about the resolution, right? How accurate? Where can I put the helicopter? How do I access it? Where am I going? When you have this type of resolution, it's a lot more accurate analysis. HLZs again, this time adding another layer of intelligence. Consider the catastrophic event, or you've got a rain event or some other environmental factors. Here you can begin to flood the scene, and because we can see beneath the canopy, find channel detail you maybe didn't know that was in existence may or may not be affecting where those HLZs are, where those avenues of approach are. Can a vehicle get me there, right? Or can my troops get there? Asset information, again, all from high altitude. Anything you can see here, you can map it. We can process resolutions from 2 to 100 points per meter. So it's like 10 centimeter imagery, but it's 3-dimensional imagery. So just to summarize, because I'm going to be out of time, again, this is a wide area mapper. It is a commercial source. Everyone can get access to it. It does have multiple benefits in terms of what you can see, what you can map, and it's extremely effective in difficult land cover and terrain applications. Thank you.
Thank you. That's fantastic.
Thank you. Thank you, Mark. So we will finish this session with our third speaker, who also will start from an airborne perspective, but I think his perspective goes quite a bit further. He loves flying things. He loves slapping sensors on things that fly, but it's all kind of meaningless unless you can take all of that that's up in the sky down to the analyst. And there's lots of frontiers with AI and ML that give us new opportunities there. So I'd like to introduce from Georgia Tech Research Institute, the Chief of Space and Intelligence Programs, Eric Truitt. Please give him a hand.
Well, thank you, Chris, and thank you, USGIF. Over the past few years, the Georgia Tech Research Institute, along with the Naval Postgraduate School, have been working on some pretty cool things. One of those in particular is on behalf of the Office of Naval Research, and that's an autonomy payload that allows for collaborative flight autonomy for swarms of unmanned aerial vehicles. Now, they demonstrated this technology by launching dozens of UAVs, giving them only a geospatial box. And then they did something very simple. They sent a command and they said, we need 6 aircraft to converge over this target location at this specific time. The swarm of UAVs themselves chose which 6 aircraft would go. Those aircraft mapped their own flight trajectories, and they converged over the target location just as they were asked to do at the given time. Now, they followed this mission success with a dogfight. Now, I say dogfight because we didn't actually weaponize the drones, though we could have, because we're Georgia Tech and we can do that. But imagine, if you will, they gave the drones a ability to sense essentially a kill box and shoot, call them lasers, imaginary projectiles at the other aircraft. And so in this 10-on-10 dogfight, they were preloaded with different dogfight tactics, and the drones again chose what the best tactics were to go head-to-head. So this was another mission success, which they then followed on and went to a bigger and better task, which was supporting the DARPA Service Academy Swarm Challenge. In this challenge, each of the service academies was given 30 drones, a mix of fixed-wing and quadrotor aircraft, and they were able to upload and come up with their own dogfighting strategies. Now, once they had these loaded, they took off and they went head-to-head. They were scored. They were given tallies for number of kills. And as a Navy veteran, I'm happy to say that the U.S. Naval Academy has achieved our ongoing commitment to beat Army and has won the challenge. Sorry, Bryant. So, as we say at Georgia Tech Research Institute, this is essentially problem solved. Now, it doesn't mean it's the end of the road for developing this technology. It just means we've gotten past art of the possible. And so now we need to look at, what do we do with this technology? And my background is as an analyst in the intelligence community. I want to actually start to ask the question, so what? So what do we do for the analyst? What do we do for the intelligence community guy that's out there trying to get better collection, higher quality collection, more near real time and specific answers to problems? I want to fly these groups of UAVs or pair those up with space or ground or sea surface or subsurface assets, and I want to perform ISR missions with them. So what we really need to do is get to collaborative sensing. And that's a little bit what I want to talk to you about today. So going back about 10 years in my past, we were using some of the tools you see on the screen here to do traditional types of analytic analysis across the intel community. Now, this is just some of them, and maybe you recognize them. But what really bothered me at the time is we were doing a lot of our analysis with this tool specifically. Not quite the definition of a collaborative analytic tool. So I got a call one day from a good friend of mine, and he was working on a program, and he said, I think this is going to change analysis. I think this is really going to help us move past this stovepipe of knowledge and technique. And he said it's called GEMA. Now, I don't want you to read all the text on the screen. I put this here so the guys with the guns and the big muscles don't come drag me off and say that's classified. So this information is out in the public forum. But what GEMA was essentially, or is essentially a canvas, he said. He says a canvas that we can put blocks on them, and we'll call these components. And each of these components does a specific intelligence task. And then analysts can wire these blocks together, and they're going to press the little play button, and things are going to turn green across the screen, and on the other end is out pops an analytic result and a happy analyst, hopefully. And I said, that sounds really cool. And he says, but wait, there's more. He said, we're also going to make this collaborative. So when you build an analytic model, it's going to be shared and visible by all of the other analysts that use this. And I said, that sounds great. He says, but wait, there's more. He says, we're also going to allow you to put models within models, so you can nest these things and build simple components, but at a high level, you'll have very transparent analytic workflows. And I said, sounds great. So we used this for several years, and it was highly successful. It's a great tool. But those nested models looked a little bit more like this, as my colleagues love to tell me about some of my models. And so it wasn't quite as transparent, or maybe even as collaborative as we'd hoped, because there was still a learning curve. People still had to dive into all this data. And then there was this other problem that was highlighted to me once when I had a phone call from a soldier out in Afghanistan. And he said, I've been using one of your models for weeks. It's been great. It's helping us win the fight. But today I went to run it, and things turned red. It didn't work. So he tells me the name of the model, and I haven't seen this model for years. I honestly hadn't touched the model in years and it was still doing great things. But what it highlighted was that the analysts were creating thousands upon thousands of models. And in this community of thousands of analysts, we actually were creating hundreds of thousands of models. But we weren't taking the time to go back and actually update those models. We weren't taking the time to make sure that every single system upgrade actually kept the models working. So again, it's a great tool, it's doing great things, but we needed a little bit of help. So as I was doing this work in my community, I got another call from a friend of mine, and he said, hey, we're starting up this thing down south of DC, and it's called the Advanced Campaign Cell. And what we'd like to do is bring all of these analysts from the multi-int community, from each intel agency, together, and we're gonna solve really hard intelligence community challenges. We'd like to take those GEMMA models you're making and capture those analytic techniques so that we can share those with the rest of the community. And I said, I'd love to help. And so we had some great mission successes. And one of those successes in particular spurred another phone call. Notice I'm keeping with a text here so I don't get drug off the stage. So this is from NRO, and they said, hey, we have this program called Sentient, and what we'd like to do is promote some of these great techniques up to where they can actually help us do better collection. And so I said, love to help. So we did that also. And again, it worked. And to this day, I still see some of the original models that we put and promoted into Sentient providing great intel value. But interestingly enough, I haven't talked to the Sentient guys myself about my models in 3 or 4 years. So we're back to this same challenge, refresh. And I'm not saying they're not keeping it up to date, because I know they certainly are, but the work that I've done and the types of things I've learned since then have not gone back into this. So how do we get to the point where the analysts remain an active part of these great tools and systems that we've been putting in place to do better collection and to execute the mission better? We believe that to do that, we need to start seeing a little bit more human-machine collaboration. Now, I'm not going to spend too much on talking about what that is. Dr. Hanna spoke about it earlier, a great example of that, and that's Google's AlphaGo system. Now, the AlphaGo system took one of the most complex human-played games in the world, and it took a problem that people said that AI couldn't solve. Great, it can do Jeopardy, great, it can do checkers, great, it can do chess, but can it do this? And they figured out that the way to do it was through using the human players and having the machines learn from them, along with the traditional AI. But it's something else that Google has been doing for years, and something that you do every day that I think is what's going to change the intel community. And it's this, Google search. You see, when you go to Google search, the machine watches you. The machine watches what you type, it watches how you type it, and then it solicits very implicit feedback unobtrusively to you to understand how well it's performing. So as it makes suggestions, as it offers search results, it's giving feedback to how well it's doing. And it can offer you better results next time. And so I imagine a world in the intel community where we put this type of technology behind all of the processes within the intelligence cycle. We put it behind the tasking and requirements folks. We put it behind the oversight and compliant folks. We put it behind the analysts, the signal processors, the reporters, the decision makers. And we let the machine watch the types of techniques that they use to perform their job each and every day. And as it watches those techniques, it can offer suggestions, it can offer to do back-end enhancements, it can look for other data sources, and in general, help them to do a better job at the daily tasks that they're performing. So let's look a bit in the future now, and let me tie this back together. So I imagine a day not too long from now where an analyst is going to come in to work, and she's going to sit down at her desk, and there in front of her is going to be the most precise, high quality, and high volume amount of intelligence data that she's needed to solve her problem than she had seen before. And that's not going to happen through magic. That's going to happen because sometime, maybe a week earlier, as the machine was watching her perform her daily tasks and do analysis in the tools that she's comfortable using and in the tools that she needs to get her mission done, it's going to have watched what were the best techniques. And when the machine offers suggestion, it's going to note where things improved and which ones she accepted and which ones she rejected. And as it does that, it's also going to look across at the other analysts. And it's going to look at people through the reporting chain. And it's going to understand the value of how those techniques are affecting others. And it's going to start to combine those efforts into more focused techniques. And then it's going to do something else. It's going to start to promote these up to the national level, to those sentients of the future. And it's going to say, hey, the analysts are using this type of data, and they need more of it, because I can tell from what they're doing there's gaps. Or I can tell from what they're doing, if I could train just a little bit better in my machine learning with this type of data, I could offer a better solution. So what's going to happen then is the sentient type tool is going to then use that to collect more data, and more precise data, more focused data for what the analytic needs are. And as it sends that data back down through that chain, through the analysts, to the reporters, it's going to get the feedback, again, unobtrusively. And it's going to note the quality of it. And as it starts to see how well that's happening, then it's going to promote that data to another level. And this goes back to where I started at. It's going to say, hey, you know, there's some great sensors out there in the tactical community that are really there on the ground. They're really there helping fight the fight. And it's going to send this type of information, these techniques, these gaps, this understanding of the mission needs of the analyst and the reporter to answer the questions that decision makers are having every day. And on those platforms, on those unmanned area vehicles, on those space vehicles, on those ground, surface, and subsurface vehicles, you're going to have decision support systems, payloads, like the one that we have for the autonomous flight, which is about the size of a credit card, and it's getting smaller every day. And those systems are going to receive updates of this type of information prior to flight, and maybe even in flight. And they're going to be able to collaborate with each other without an operator in the loop. And they're going to be able to go out, and in some cases, as we've helped the Office of Naval Research with, they're going to be able to launch dozens of these things off the side of Navy ships. They're going to fly into hostile territory and places where there's humanitarian needs, and they're going to go out and perform a mission to a level we've never seen. They're going to bring back data to the analyst, to the reporter, to the national and tactical decision maker that's of a higher quality, it's of a better timeliness, it's had pre-processing because it understands what the analyst is going to do with it when they receive it, so they'll be able to pre-process some of this stuff. And it's going to help us win the intelligence challenges and battles of the future. And that's the type of research that me and my colleagues are heading towards now. That's how we're going to make use of this great technology of autonomous vehicles and collaborative mission execution. We hope that you will follow us on this journey and be a part of it. And I thank you for your time today. And if you want to talk more, please catch me at the booth. Thank you.